All right, here we go. Y'all excited? Always. Okay. Welcome to the wonderful world of trigonometry. We're going to just start out today with a few things that we've already done. Okay, I want to review that 30, 60, 90 triangle, that 45, 45, 90 triangle. So let's start with that real fast. Not going to spend too much time on it. Can somebody tell me where the 30, 60, 90 triangle comes from? Like, how did I create it? Do you remember? We took an equilateral triangle and cut it exactly in half. So the other half of the equilateral triangle will be over here someplace, right?
Yeah.
And then we picked a measurement that we could cut in half real easily. What measurement was that? 2. So the sides would be a 2 here and a 2 here and a 2 on the bottom. But when we sliced down the center of this equilateral triangle, not only did we slice this 60 up here in half so that it was 30, 30, but we sliced this 2 in half so that it was 1 and 1. And I gave you a little quote on the board. I'm not going to write it again now, but I'll say it again now. And I put it in quotes. It took like 3 lines on the board. You wrote it down, I hope. And it said, in a 30, 60, 90 triangle, the side opposite the 30-degree angle is always half the hypotenuse. And that's really important to know because that means that the sine of 30 is 1/2. And there's all kinds of other measurements like that as well. But let's just get back to this one. What's this last leg if I did the Pythagorean theorem on this right triangle?
Square root of 3.
Square root of 3. Very good. Okay? And what about the 45, 45, 90 triangle? Where does that come from? Comes from a square. Taking a square and cutting a square in half along its diagonal. Right? So I'm just going to build a square. And with a square, all 4 sides are the same, all 4 angles are the same. So the best number to put there is what? They're all the same. 1 to 1 to 1. Ratio is 1 to 1 to 1 to 1 of all 4 sides of the square. You draw your diagonal, and the diagonal splits both of those 90s exactly in half. So I have a 45 up here, I have a 45 here, 45 here, and a 45 here. Of course, I'm only interested in half of that picture anyhow, so I'm just going to draw the other half down here. So this is 45, 45 degrees. These sides are congruent to each other, but I didn't need to mark the fact that they were congruent because the angle's congruent means the sides are congruent. If I mark the sides congruent, I don't have to label the angles because there's no other way that those angles could be anything but 45 each. Does that make sense? So I'm just doing that this time, but in the future I'll probably just go doop, doop, and you'll have to know it's a 45, 45, 90. The isosceles right triangle is a 45, 45, 90 triangle. The ratio of the sides, 1, 1, square root of 2. Okay? Be careful because in this triangle, the square root is on your hypotenuse, but in this triangle, your square root's not on the hypotenuse. However, what is common about the hypotenuse in both of them? The 2 is involved on the hypotenuse in both of them. So, yeah, see what it is. You can figure out the hypotenuse is the largest side of this triangle because 2 is really the square root of 4, and square root of 4 is bigger than square root of 3. And these are square roots of 1. Square root of 2 is larger than square root of 1. So the hypotenuse is always the largest side. Kills me when I see people put a 1 here on the hypotenuse, a 1 here, and a root 2 down here. Okay? Please don't do that. All right, so that's a quick review of our 30, 60, 90, and our 45, 45, 90 triangles. I want to discuss with you just a little bit about where these trig functions come into play and why they exist the way they do. I am going to create an angle on the board. Give me a degree measurement.
63.
63. I am going to create a 63-degree angle in a right triangle. And if this was a perfect world, I'd be passing out protractors and rulers and everything for you guys to do this all yourself, but it's not. It's my world, so I want to do it up here, right? So I'm going to create a 63-degree angle. I'm going to do that by starting with a ray. A ray has an endpoint and continues forever and ever and ever, right? Now I need another ray, but I want those 2 rays to be sharing a common endpoint, which will become the vertex of my triangle, and also I want the angle in between those 2 rays to be 63 degrees. So I'm going to take my little protractor, I'm going to come on up here and put the vertex where it belongs, and I'm going to measure 63 degrees. So starting from here, 10, 20, 30, 40, 50, 60, 1, 2, 3, 63. I'm going to hold my chalk there, push that up there, and there's my 63 degree angle. you this before, but I'm going to make this into a right triangle. So either off this end or off this end, side, you should say off the bottom side or off the edge up here, I need to create a 90-degree angle. So then I can do it anywhere I want. So I think I'm going to do it up here. I'm going to pick a point like this point right here, and I'm going to create a 90-degree angle off that point using the edge of the angle that I already have. So my vertex is going to go up here, and I'm going to create a 90-degree angle. Here's my 90 mark. Okay, this time I'm just going to freehand it, okay? I'm going to go from here down, and obviously I'm not forming a triangle yet, so remember I said this can keep going? I need to keep going until I get that side. It's no big deal. I'm going to trip over this box pretty soon, and that'll be on video. It'll be funny. Okay, so let's move it. All right, so this is definitely 90 up here. How much is this? How much?
27.
How do you know that?
You add 90 and 63 and
So what's the big idea that lets me know it's 23?
you added 2 angles and then subtracted it
So the 3 angles of a triangle, half the total?
from 180.
180, okay? And if you have a 90 already to begin with, then the other two make 90 together as well. Okay, and there's a theorem that you had in geometry that said in a right triangle, the two acute angles have to be complementary. Do you remember that theorem? It's been a while, I know, since you took geometry. But this will be 27, and I can figure that out without even measuring it. All right? But if I put this up here, it better be close. And it's off by a little, looks more like 29, but you got to give room for error because I did freehand that last side, and I am working with chalk, and I'm not really perfect up here. Okay, so here's the deal. If I measured, let's say this side, and I had a measurement here, and I measured, let's say this side, and I had a measurement right there, and I compared the two, and whatever I get when I divide A by B, and I pop it in the calculator, get a decimal, okay, I'm going to get the same thing as if I had done this again, if each one of you have done it, but come up with a different size triangle. So for instance, what I guess I'm trying to say is, what if I had picked this point to make my right angle? I'd be coming down here, wouldn't I? Oh, not like that. I'd be coming down like this, wouldn't I? That would be my 90, this would be my 63, and this would still be 27. Well, maybe this is J and this is K. Well, you compare J to K, and you're going to get the same answer that you would have with A and B. Additionally, what if somebody didn't start with the 63? What if somebody started with the 27? If somebody created a 27-degree angle, a really big 27-degree angle, and I'm going to eyeball it, 27 degrees, maybe put their 90 up here like this. Here's your 90. That would make this up here how much? 63. Okay, now be careful where I'm going to put things, right? I'm going to put my R and S like that. And if I compare the R to S, I'm going to get the same comparison. Can you see what I'm doing? Anybody noticing it yet? If I'm at this 63, if this is the perspective from which I'm coming from, and I did this stick figure with you on the board and talked about perspective, right? If I'm at this 63 and I compare R to S, I'm performing the sine function, aren't I? That's what I'm doing. And over here, if I'm at the 63, this is where I am, and I compare the J to the K, that is the sine again, because this is opposite over hypotenuse. And if I'm over here at this 63, got it, 3 different size triangles, but if I'm there and I compare the opposite from where I am, which is side A, to the hypotenuse, which is side B, all of these fractions are made with different numbers. A over B, A is a number that's different than B, that's different than J, that's different from K, that's different from R, that's different from S, but when I reduce those fractions, I always get the same ratio. I always get the same ratio. And those ratios are stored in your calculator. Every single time you're going to do this. So the sine function compares the opposite leg to the hypotenuse. But you've got to tell the calculator where you're standing. It has to be from a 63-degree angle, because if I was at the 27, I'd have a different ratio, wouldn't I? So anybody pop a calculator and get that sine of 63 in there for me? I'll tell you one thing about it, it's less than 1. 0.89.
0.89.
Okay. Why did I know it was less than 1? I need a thinker. Jalen?
Because it's less than 90 degrees.
I need more. I need a thinker. Michaela?
Because it's half of your hypotenuse.
Okay, so you're getting at the idea. It's not quite half because this isn't a 30-degree angle. Okay, so we're not in the 30, 60, 90 triangle, but we are comparing a side, a leg, to the hypotenuse.
Oh, isn't the opposite leg half the hypotenuse?
I think I just heard that. Which is what she just said. Okay, now that's true only in your 30, 60, 90 triangle. So I need a thinker. Okay, do you mind smacking him for me? I need a thinker. You're my thinker. Why is the sine of 63, according to all these pictures, always going to be less than 1? Edie?
Because since like the leg that you're comparing is smaller than the hypotenuse, when you divide that by a bigger number.
Does that make sense?
Yeah.
No? Put it in your words. Were you going to say something? Never mind. Say it again then, Edie, louder, so they can hear you.
Because the arm, what is that, a leg? Right? Because the leg is smaller than the hypotenuse, which is longer than it, dividing a smaller number by a larger number is going to get you a decimal.
Yeah, it makes sense.
Does it make sense? Say it in your words, so they can hear. Raina.
Oh, she basically said because the length is smaller than the hypotenuse, so since you're dividing a smaller number by a bigger number, it would be less than 1.
Wait, why is there?
It's not an improper fraction, so therefore it will be more than 1.
Right, so it's a proper fraction. The numerator is always going to be smaller than the denominator, because the denominator is your hypotenuse, so it's the biggest side of the triangle. Yes? Yeah, right up. Pass that one, please. Okay, so what am I trying to tell you? I'm trying to tell you that in your calculator, the sine of 63 is stored. It never changes. It's in all your calculators. Anybody punches the sine of 63, they're going to get this answer. So, if I knew I had a 63 here, and I knew my r, but I didn't know my s, wouldn't I be able to solve for one or the other? If I knew my r, but let's say I knew my r, but I didn't know my s, this was a question mark, wouldn't I be able to like cross multiply and do some solving for what I need to know? So I just think it's really cool that no matter what angle measurement you're at in a right triangle, of course I'm talking about the two acute angles of a right triangle, no matter what angle measurement you're at, those ratios of sine, cosine, tangent, sine, cosine, tangent, those are the three that are on your calculator, but cotangent, secant, cosecant can be done there too. Is it block up there? Yeah. Okay. And like I said, they're stored there. We're going to use the calculator a little bit to try and get these out. These are not exact answers. Do you understand me? The calculator is not giving you an exact answer. I know you're saying, oh my God, they go all the way down to like the 9th or 10th decimal place. You can't get any more exact than that. But yeah, you can. Right? So what I'm going to do with you now are some questions that I'm going to ask you to give me some exact answers. The logic still follows. I'm not going to use the calculator, but I want you to understand the difference of when you're going to get an exact answer and when you're not going to get an exact answer. So you've got to follow those directions that are given to you when the worksheets do come at you, okay? All right, a couple of examples with you, and we're going to incorporate the 1, 2, 3 things that we've learned so far. Hopefully we've learned our 30, 60, 90 triangles. Hopefully you have learned how to manipulate something in terms of pi, and hopefully you've learned how to sketch an angle in standard
Oh, thank you.
position. Okay, so we're gonna do all that together. Add one more thing, we'll actually evaluate the trig functions with exact answers. Okay, so I'm gonna start you off with a real easy example, and we're gonna say that theta is pi over 6. Theta is pi over 6. We're gonna graph this angle in standard position. We're gonna create a reference triangle for this angle, and we're going to evaluate all of the 6 trig functions for this, and also identify what the reference angle would be, alpha. Okay, so what is pi over 6? Can you tell me what quadrant we're in? You're in the first quadrant, you're in the second quadrant. Which is it?
First.
Okay, so let's take a peek at it. If I went from beginning, we always start at the positive x-axis, and I rotated this sucker all the way around, 180 degrees, this would be pi. So I want pi over 6, which is the same thing as 1/6 of pi. I want to cut this into 6 pieces. It's already cut in half. What do I have to divide this section by? I need to divide this by 3 and this by 3. And that'll give me a total of 6 pieces, right? So 1, 2, there's 1, 2, 3 pieces there. I do the same thing here, and there's 1, 2, 3 pieces there. Looks like a sunburst. Okay, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, and 6 pi over 6, which is 1 whole pi. Okay. So now you know where 1 pi over 6 is? Okay, so I'm going to just draw 1 pi over 6. Oh, I guess I shouldn't do that yet. Okay, and this angle measurement right here is pi over 6. This is my theta. Okay, now what's your alpha? Say it again?
30 degrees.
Your alpha is 30 degrees. It is the same thing as your theta in quadrant 1. So you got the fact that pi over 6 was 30 degrees off the top of your head. How?
By dividing 180 by 6.
180 divided by 6 is 30 degrees. So that's pretty simple. Okay, so in quadrant 1, your alpha and your theta are the same thing. So it doesn't matter to me whether you write alpha or theta. And you could even, if you feel like it, put alpha equals theta equals alpha in this case. Okay? Okay, when we get into a different quadrant, they'll be different. But right now in quadrant 1, they're the same thing. So, I want you, I'm going to draw this a little bit longer to get out of my mess there I made, with all that writing in the middle. I want you to pick a point on your terminal side. This is your initial side, this is your terminal side. Pick a point on your terminal side and draw a perpendicular line to the closest x-axis. And the closest x-axis is, of course, the one right next to it, right here. So you're going to go down, you're going to draw perpendicular and form a 90. Now, this is a 30-degree angle. What are the ratios of the sides of a 30, 60, 90 triangle all the time?
1 to 2 to the square root of 3.
1 to 2 to the square root of 3. So I think in my mind, the sine of 30 is 1/2. So the side opposite the 30 is always half the hypotenuse. I put my 1 here on my short leg, I put my 2 on the hypotenuse, and I throw the root of 3 down there on the long leg. They have to be in that order. All those numbers are positive because you're in quadrant 1. Now let's answer the questions. I say sine of theta, you say cosine of theta. Right? I say tangent of theta, you say cotangent of theta. I say secant of theta, you say cosecant of theta. In that order. Might have already gave away the first one. What's the sine of theta? Here's my theta. And here I am, okay, if anybody wonders where that stick figure is, that stick figure is always right home at 0, 0 at the origin. So from here, sine compares what to what? What do I get? What do you get?
So,
Then you get 1/2, okay? So the sine of, I think maybe I'll just write sine of 30 degrees for you. I'll do it again. You don't have to redo it if you want, you can just put 30 degrees right there. But I like to be specific if I'm going to, and it really doesn't really matter if you use 30 degrees right here for me, or you want to write pi over 6. Chances are you're going to see me putting things in radian form more often than not, okay? So this gives me 1/2. What is the cosine of 30 degrees? The cosine of pi over 6?
Square root of 3 over 2.
Square root of 3 over 2, because the cosine compares the adjacent leg to the hypotenuse, square root of 3 over 2. And it's always a square root of 3 over 2. If you were to type the cosine of 30 on your calculator, it'll give you this decimal. And then if you type the square root of 3 divided by 2, it gives you the same decimal. They are equivalent. Square root of 3 over 2 is exact, but the decimal's not exact. So be careful when the question is asking for exact answers. It wants the square root stuff. Tangent of 30. 1 over the square root of 3. Tangent compares the opposite leg to the adjacent leg. You can't leave it like that though. I expect you to rationalize that. Square root of 3 over 3. Cotangent. Anybody know a trick? Reciprocal of what? Reciprocal of 10. Okay, these bracket up. What's the reciprocal of either one of those? I don't care. Yeah, just the square root of 3. I'm going to call it the square root of 3 over 1, which is the square root of 3. Secant of 30 degrees. 2 over root 3, which you cannot leave like that. You're going to call it 2 root 3 over 3. And cosecant, just 2. Notice I put the brackets up there, and I liked your word. They're reciprocals. They're reciprocal functions. Okay, learn them in order. All right, I'm going to get tougher with you. You ready? I am with you. All right, so here's example 2, and I might even erase and do a little bit more. I'm going to go a little faster too, and pick up the pace. So my theta in this case is going to be 3 pi over 4.
that was on the test.
What?
That was on the test.
That was on the test. Oh no. Okay, 3 pi over 4. 3 pi over 4. What quadrant are we in?
Third.
No, quadrant 2.
Two.
I'm in the second quadrant. Okay, who can explain in a really good way why?
It's more than half.
It's more than half. What do you mean?
Oh,
It's more than half of the word.
because it's 3/4.
Okay,
It's
so,
4.
It's 3/4.
okay, so it's more than halfway of pi?
Yeah.
Yeah, because it's.
So I like the fact that I'm hearing there's 4/4, okay, of pi to get you all the way to pi. Then this is what I'm looking for your logic to be like. I'm looking for you to say, well, 3/4 pi is almost 4/4 pi, and that would be a full pi. But I'm not quite there. So I'm a little bit shy. I must be in quadrant 2. Okay, let's go through this again. This is pi, right? Way over here. This is pi from beginning to over here. This is 4/4 pi. 3/4 pi is not quite 4/4 pi. You're a little bit shy. So you're not in quadrant 3. You haven't gone past there, and you're shy of it, which means you're up here in quadrant 2. Now, I need to draw this angle up in quadrant 2. I need to take pi and divide it into 4 pieces. Well, it's already divided in half right here, right? So now all I got to do is take each half and cut it in half again, and that'll put the whole pi divided into 4. So, all right, just like I did over there. Instead of dividing into 6s, I'm dividing into 4ths. So this is 1/4 pi, 2/4 pi, 3/4 pi, and 4/4 pi. So that's what you meant, right? And Anastasia, Fantasia. So that you're past half the way mark? Okay. Alrighty. Here we go. So where's 3 pi over 4? This mark right here, right? Alright. So I got a lot of stuff going on here. I just want 3 pi over 4 right there. Boom. Here's theta equals 3 pi over 4. That's my theta, the big angle that brings me from my initial side to my terminal side. How big is my alpha?
45 degrees.
My alpha is 45 degrees. That's my reference angle. It's 45 degrees. So you can actually mark it in here if you want. You don't have to put alpha, you can just write the 45, it's your choice. And now, like we did in this previous problem, you're going to pick a point on your terminal side, and you are going to form a line that goes perpendicular to the closest x-axis. So I don't care where on this side you want to be. If you want to be really close, everything's going to be really jammed. I'm not going to be able to understand what you're doing. So get away from the vertex a little bit. Bring yourself up here someplace. And draw a line perpendicular to the closest x-axis. Where are you going to draw it? Give me a good word. From here, where do I go? Down. Down. Down is the word I want. Okay? Down. When you go perpendicular, you form a 90-degree angle. Now you have a 45, 45, 90 triangle. The ratio of the sides are no longer 1, 2, root 3. The ratio of the sides are now
1, 1,
1, 1, root 2. And both of the legs get your 1s, and the hypotenuse gets your root 2. Now, one little tidbit has to get into play right here that I didn't have to pay attention to in quadrant 1. And that little detail is the fact that this particular one has to have a negative sign on it. Can you understand why it would need it? Yeah, I mean, if we're moving along the x-axis to the left, we better be talking about a negative value. Okay, and then this one's positive because I'm still going up, so I still have a positive one. And by definition, always leave your hypotenuse positive. Never put a negative on the hypotenuse sign. They're always, always positive. All right, now we're doing the sine of 3 pi over 4. We're doing the cosine of 3 pi over 4. And so on. Why don't you guys set your numbers up like this? You should get to the point where you don't have to look or copy from the board. You should be doing it yourself. Go ahead. What's the sine of 3 pi over 4?
Root 2 over 2.
It is root 2 over 2. Okay, most people are going to think it's what first?
1 over 2.
1 over root 2. Let's not forget, your perspective that you're evaluating all of these functions from, and they are functions, is right there at home. So there you are, and you want to compare the opposite leg to the hypotenuse for the sine function. So, do I have to write SOHCAHTOA on the board anywhere? Okay, it's okay with SOHCAHTOA? Okay, good. All right. So opposite leg is a 1, hypotenuse is a root 2. This rationalizes to root 2 over 2 when you rationalize your denominator. Okay. Cosine of 3 pi over 4.
Negative root 2 over 2.
Because it's a negative 1 divided by root 2. Which is negative root 2 over 2. Easier now. Tangent.
Negative 4.
Negative 1. So I'm going to write 1 over negative 1 and then say negative 1. This tells me you're doing your work. And this tells me you can evaluate it as well. Cotangent. Also negative 1. True. Secant.
Negative root 2.
Negative root 2. Give it. Cosecant.
Root 2.
Cool. So far, so good? Want to go faster? Can't go that fast. Okay, so I have 2 angles for you to try for tomorrow, okay? One of them is going to be, I'm gonna put this right here in the middle of the board. One of them is gonna be theta equals, let's go for, 4 pi over 3, and the other one will be 11 pi over 6. So what do you have to do for each one? You need to sketch it, figure out what your reference angle is, build your reference triangle. You will either get a 30, 60, 90 reference triangle, or you will get a 45, 45, 90 reference triangle. You will label the sides, and you will evaluate each one of the 6 trig functions. Do not forget your plus or minus, and make sure to rationalize all denominators. Okay? You got me? Tell it out. And yes, it is.